This is the first of several videos on graphing rational functions. But before we can actually get to graphing a rational function, let's get the definition out there. A rational function is a function that can be written as n of x over d of x. It's just a fraction where you have a polynomial on the top and a polynomial on the bottom. And this notation is just your function notation. I'm using n instead of f of x because n stands for numerator and d stands for denominator, but you could use whatever letter you want. It's important to note this, that the denominator function cannot equal 0. You know that you cannot divide by 0. Which leads us to the idea of domain. The domain of a rational function of x includes all real numbers except the x values that make the denominator equal to 0. We looked at domain in a previous video, but we're just going to look now at the domain of a rational function. Let me be sure you understand the idea of what a domain is. Domain is just all of the x values that you can use in the function that make sense. Like I just made a little t-chart here. If I put 0 into this function, I'm looking at 0 minus 5. This would be 1 over negative 5. That is a reasonable answer. Put 1 in here. 1 minus 5 is negative 4. This would be negative 1/4, etc. I can plug all of these numbers in and get a reasonable answer for y. But when I get to 5, I've got a problem, because if I put 5 in here, 5 minus 5 is 0. I'm looking at 1 over 0. We can't have 0 in the denominator. That would be an undefined value. So our domain will be all of these x's that when I plug them into the function, I get a reasonable answer. The idea of domain is for us to eliminate any values that create 0 in the denominator. So we need to exclude from the domain all values that would produce a 0 in the denominator. So let's take a look at another one here. Here's a function a little more complicated than the function on the previous screen, but what's important is to look at the denominator. We want to exclude the values that will create 0 in the denominator. So to do that, we are going to set the denominator equal to 0 and solve. The good thing about this function is that the denominator was already factored. So all I have to do is take each part and set them equal to 0 and solve, getting these three numbers. These are the numbers that need to be excluded from the domain, because if I put any of them into the denominator, I'm going to create 0 in the denominator. So there's two ways for me to express a domain. One is to write it in set builder notation, which is really the easiest way, but some books require the interval notation down here. So the set builder notation is the set of all x such that x does not equal 0, 2, or 5. The other way to look at this is the interval notation. Now you have to think about there being a number line, and what we've done is we have eliminated 0, 2, and 5. So coming in from this direction, all the way down here from negative infinity, all of these numbers in here are good until we get to 0. 0 itself gets thrown out. That's why there is a curved parenthesis here. Then to get this little interval, we're going from 0 up to 2, with a hole being on 2. Then from 2 to 5, same idea, there's a hole at 5, and then from 5 on down. New function, we're going to set the denominator equal to 0 and solve. We just get x equal to 4. So the domain is going to be all x's except 4. So there's your set builder notation, all x such that x does not equal 4. Here is the interval notation. Here's a number line. This is showing that 4 itself is being excluded. So our domain is all of this stuff leading up to 4, and that is this portion, negative infinity to 4 with a curved parenthesis because 4 itself is not included. And then it stops because there's a hole, and then we pick up again going this direction, and that's our 4 out to positive infinity. Next one, x squared minus 4, set it equal to 0. Now to do this one, I'm going to have to factor this out. The previous ones were either factored or they didn't need to be factored, but to solve that quadratic, I need to factor it. Once it's factored equal to 0, I can set those equal to 0 and solve. So those are the numbers that are going to get excluded from my domain. Every other number you can think of can get plugged into here and give us a reasonable number in our t-chart, except negative 2 and 2. So there's your set builder, all x such that x does not equal negative 2 or 2. And there's our interval notation. Take a look at your number line. Those circles there indicate the holes that occur at negative 2 and 2. So All of this leading up to -2, that's from -infinity to -2. Then this portion in here is from -2 to 2. And then from here on out, it's 2 to infinity. Notice curved parenthesis everywhere. Infinity and -infinity always get a curved parenthesis. This is getting a curved parenthesis because -2 itself is not included in the solution set. It can't be included in the solution set. That's where the hole is. This is what's telling me that -2 and 2 cannot be part of the domain. Set this denominator equal to 0. And notice I just keep talking about the denominator because there's nothing I need to worry about. The numerator can be 0. It's the denominator cannot be equal to 0. Set this equal to 0 and try to solve this. Subtract 9 from both sides, and here I've got a problem because to solve this I would need to take the square root of both sides. But that means I would be taking the square root of a negative, and that produces an imaginary answer. So there are no real numbers that cause the denominator to equal 0, which means the domain is all real numbers. There's nothing I'm going to exclude. And in terms of interval notation, it's just -infinity to infinity. The discussion of domain leads us into this idea of what's called an asymptote. This is a graph. You could type this into your graphing calculator. I put it in the graphing utility in my computer, and this is what I get. I get this curve, I get this curve. This yellow line right here is what's called a vertical asymptote. Notice these little curves do not cross the line. They come up real close. This is getting closer and closer and closer, and if we went here where you can't see, you would see this just barely a smidge off of the line. And that's the idea of a vertical asymptote. The definition of vertical asymptote is where the graph increases or decreases without bound as x approaches A. A is this right here. A is my asymptote right here. So this is getting closer and closer. It's increasing without bound. This coming in from this direction is decreasing without bound. That's what creates this to be an asymptote. Now, when you type into your calculator, the asymptote does not necessarily show up. It depends on your calculator and what your mode is, but generally this doesn't show up. I've just highlighted this to show you what happens with the curves. You don't know where these curves come from yet. You will. All we're doing right now is plugging these into a calculator to take a look at them. This has one asymptote. Where does it have an asymptote? It has an asymptote right here at the line x equals 0. Think about that. If x equaled 0, we would be looking at this expression, 1 over 0, which is undefined. We're getting our asymptotes where the x value makes the function undefined. Let's take a look at another one here. X squared minus 4. This is just typed into the calculator, but notice we have two asymptotes occurring here and here. That happens to be at 2 and at -2. So take a look at all of these curves. This is getting closer and closer to the asymptote, and this is taking off, increasing without bound. Over on this side, decreasing, decreasing over here, increasing coming in from this direction. So those are our vertical asymptotes. This shows you that it's possible to have more than one vertical asymptote. Notice that our curves do not cross or touch those asymptotes. That's the idea of the asymptote. Because certain values are excluded from the domain, their graphs have holes or asymptotes. I'm only talking about asymptote right now. Holes a teeny bit different. An asymptote is a line that the curve approaches. The curve cannot cross a vertical asymptote. So if we have a function, p of x over q of x, remember a minute ago I used n of x and d of x. It doesn't matter what letters I use here. If this is a rational function, and this is important, if p of x and q of x have no common factors, and a is a 0 of q of x, the denominator, then x equals a is a vertical asymptote of the graph. So we end up with x equals 2 as a vertical asymptote. And look, we did the same thing to find the vertical asymptotes as we did to find the domain. It's just that the terminology is a little different for what you express. The domain is all x such that x doesn't equal 2. So that's being thrown out. On the other hand, if you're asked to name the vertical asymptote, you say it from a positive perspective and say, okay, the vertical asymptote occurs at x equals 2. And here's just a picture to show you. Here's our curves approaching and taking off without bound that way, approaching from this way, taking off this way, which is decreasing, and there's our vertical asymptote of x equal 2. Let's find any vertical asymptotes here. We're going to set the denominator equal to 0 and solve, and to do that, I will factor the denominator as x plus 3 times x minus 3 equal to 0. If I solve those, that's where I get this plus or minus 3, and you're looking at a picture of the two asymptotes and the curves. You'll know later on how to get these curves plotted in here. All we're doing right now is talking about the asymptotes. Set this equal to 0 and solve. Well, we talked about that a little while ago with the domain. There's no vertical asymptotes here because when you solve this, you end up with an imaginary value. There are no vertical asymptotes. Take a look at what the graphing calculator shows you on the curve. There's no place where this snuggles into the vertical line and then takes off. It just runs smoothly, almost like a horizontal line.